Hello, everyone. My name is Wrya Kadir. I'm a research fellow at the University of Bergen, and this is a joint work with my supervisor, Trombetti and Ferdinando Zullo from the University of Campania. Today, I'm going to talk about interpolation-based decoding of MRD codes. This is based on three research that can be found in the abstract in the website. This is an overview of my talk. I'll start with some basic terminologies that they already been mentioned by two other speakers, and then definitions of rank metric codes, new MRD codes, and then I'll talk about the interpolation-based decoding algorithm for these new MRD codes. At the end, I'll mention how to reconstruct the error vector in these decoding algorithms. Let Q be a power of prime, and we denote a finite field extension of degree n with FQn. We have a definition here. A Q polynomial or linearized polynomial is a polynomial of the form that can be seen here. In this form over Fqn. If ak-1, the coefficient ak-1 is not equal to 0, then we say that L of x has Q degree k-1. And the set of all these polynomials is denoted as LKFQ to power n. By kernel of L, we mean the set of roots of L of x over Fqn, and by rank, we mean n minus the dimension of its kernel. Dickson matrix and these proposition play a main role in the decoding process. So let L of x be a Q polynomial over Fqn with rank t. Then the associated Dickson matrix in this form that can be seen here has two nice properties. The first one is, since the linearized polynomial has rank t, so this Dickson matrix will also has rank t. And the second nice property is that for any t by t submatrix formed by t consecutive rows and t consecutive columns of D, is non-singular. So it's these two properties, we will use them later. And for simplicity, we denote q to power x to power q to power I with x to power square bracket I. Let A be a vector of length n over Fqm, and by rank of A, we mean the number of linearly independent components of A over Fq, and the rank distance of two vectors is the rank of their differences, and this distance defines a metric which we call it rank metric. So and this rank metric we can define a code based on this metric. Rank metric code is a subset of Fqm to power n with respect to rank metric, and the minimum distance of the code is the minimum non-zero distance between its components, between its vectors. Similar to a Hamming metric, we also have a singleton-like bound, and if a rank metric code attains this bound, we call it maximum rank distance code, or MRD codes in short. Gabidulin codes were introduced by Gabidulin, Delsart, and Roth independently, but we know them as Gabidulin codes. They are the most famous MRD codes that actually, this is what we know. So Gabidulin codes are evaluation codes, and the Gabidulin code with length n and dimension k over Fqn is the evaluation of the linearized polynomials of the form that can be seen here on Fq linearly independent points alpha 0 to alpha n-1. In Hamming metric, these evaluation codes are the evaluation points are distinct points, but here the evaluation points are linearly independent points over Fq. And Gabidulin codes are Fqn linear MRD codes, which means they are linear over the main extension field. And the size is q to the power nk, and the distance is d equal to n minus k plus 1, since they are MRD codes. And Gabidulin codes are kind of rank metric analog for resolving codes. And syndrome-based decoding can be efficiently applied to decode Gabidulin codes, which was proposed by Gabidulin. But since the work of Wrya K, a number of new MRD codes were constructed, or it's better to say a number of new twisted MRD codes were constructed. We have been working on these new MRD codes and especially working on the decoding algorithm of these new MRD codes. So far, we are only able to decode MRD codes with these forms. So the evaluation of these kind of the set of linearized polynomial in this form. F0 and Fk should satisfy a certain conditions for the code to be MRD. So the conditions are based on F0 or on F0 and Fk. I mean these two coefficients of the linearized polynomial. This is the form of the linearized polynomial that I mentioned. But the conditions on F0 and Fk, for example, in AGTG codes, additive, generalized, twisted Gabidulin codes, you can say that Fk is equal to eta F0. So Fk is somehow dependent on F0 and with some extra conditions on the eta, and F0 is taken in the main extension field. I started with AGTG codes because twisted Gabidulin codes and generalized twisted Gabidulin codes are subfamilies of these AGTG codes. So if someone is able to decode these AGTG codes, they would be able to decode twisted Gabidulin codes and also generalized twisted Gabidulin codes. For the partition codes, which was again proposed by Ferro and Otto, both these codes are proposed by these two researchers. And for partition codes, we also have this condition on the coefficients F0 and Fk. You can see here I is a subset in the base field, not on the main extension field. And for Trombetti Zhou rank metric codes, which is not equivalent to the other two families, here also we have F0 and Fk, some condition on these two coefficients, and some extra coefficients on the norm of these two coefficients. But here you can see that F0 and Fk are taken from the half field. They are not taken from the main extension field or from the base field. So these are the differences between the condition on F0 and Fk between these three families. But here we realize that the syndrome-based decoding cannot be applied to these new MRD codes. The reason is because the linearity of the MRD codes plays a main role in the syndrome-based decoding. So since these codes are not linear over the main extension field, so we need a new decoding algorithm which doesn't need this linearity property to decode. So that's why we were looking for a new decoding algorithm for these new families. Let F tilde be the n-dimensional vector obtained from the message F0 to Fk-1. In AGTG codes, F tilde is defined in these form. You can see F0 and Fk. As I mentioned, F0 and Fk are somehow dependent. So Fk is defined in terms of F0. In partition code, we have two different cases. So F tilde is defined in these ways for two different cases that is defined in partition codes. And for TC codes, F tilde is defined in the following way. A and B are the elements. Actually, these two are the coefficients F0 and Fk that are taken from the half field. So now we constructed the F tilde, then we move on the construction of the code word, because we have a vector of length n, which is the extension of the message, and then this vector of length n can give the code word somehow. Let M be the Moore matrix associated with the linearly independent evaluation points alpha 0 to alpha n minus 1. So C, which is the code word, can be generated as F tilde from the previous slide, multiplied by M transpose. M, as I mentioned, is the Moore matrix associated to the evaluation points. And then to know how to add the error, we need error interpolation polynomial. Let g of x be the error interpolation polynomial. This is also as a linearized polynomial, which satisfies g of alpha I equal to ei. So the vector e, which is the vector, the error vector, is equal to g multiplied by m transpose. Then, having e and c, we can generate the received word. So R would be C plus E, which is F tilde plus G multiplied by M transpose. But here, in this decoding algorithm, instead of looking for error vector E, we first find the coefficients of the error interpolation polynomial. So these two are equivalent. So instead of looking for error vector E, we look for the coefficients of the error interpolation polynomial. The previous equation can be written in this way, because we know R, because this is a received vector. We know M, which is the Moore matrix associated to the evaluation points. So we know R tilde. So R tilde is now. I have to mention that this Moore matrix is invertible, so we can find the inverse of this matrix. So R tilde is noun. So regarding this equation, we can see, since R tilde is noun, so we can say gk plus 1 till gn minus 1, this part of the vector g is also known, because due to the form of f tilde, you can see the last part of this vector is so the last part of this vector is 0. So due to this form, we can say gk plus 1 until gn minus 1 are already known. So the rest, the task is basically finding the rest of these vector, which is g0 to g sub k. How to reconstruct g of x? How to find the remaining part? Let G be the Dickson matrix associated to the error interpolation polynomial. Error interpolation polynomial was a linearized polynomial, so we can generate the Dickson matrix associated to this polynomial. We already mentioned that it has two nice properties. It has rank t, because the error vector has rank t, and any t by t submatrix of this matrix is non-singular. So this leads us to the following recursive equation. For example, we can write GT as a linear combination of, the column GT. These are the columns of these matrices. So the column GT can be written as the linear combination of the column G0 till GT minus 1. So it will give this recursive equation. And this recursive equation, since gk plus 1 until gn minus 1 are already known, so using these known coefficients, we can generate this linear system of equation with t unknown. Lambda 1 till lambda t are unknowns, or they can be seen as the connection vector of Q linearized shift register, which was discussed in a paper by Sidorenko, Bossert, and Richter. To solve this linear system of equation, we have two cases. The first case, when the error vector, the first case here, when the error vector, the rank of error vector doesn't attain the unique decoding radius. So in this case, we have at least t affine equation with t variables lambda 1 to lambda t with rank t. So in this case, Berlekamp-Massey algorithm can be applied to find the unknowns, which are lambda 1 to lambda t.
5 minutes.
Thank you. In the case 2, when the rank of the error vector attains the unique decoding radius. In this case, we have t minus 1 affine equation with t variables. So the set of solutions for lambda has dimension 1 and can be expressed in this form. Similarly, we can find lambda and lambda dash using the idea of Sidorenko, Richter, and Bozard, which is the modified version of the Berlekamp-Massey algorithm. But here we have a free variable omega, which is unknown. How to find omega is the remaining task for solving this linear system of equations. Omega in the process of decoding AGTG codes, partition codes, and Trombetti Zhou arithmetic codes have different approaches to find. For example, in AGTG codes, we use extra relations that, as I mentioned, F0 and Fk was kind of somehow related and dependent. So we use this extra relation and kind of change the problem to solve or solve these projective polynomial. So instead of the problem of decoding is changed to the problem of solving these projective polynomial. But for partition code, we treat G0 and G codes separately as Gabidulin codes. But in Trombetti Zhou arithmetic codes, we use these two extra relations since, as I mentioned, A and B, F0 and Fk are taken from the half field. We can generate these two equations, and these two equations leads us to change the equation to solve this nice quadratic equation. So surprisingly, we changed the problem is changed to solve this quadratic equation. So you can see the differences between the decoding of AGTG codes, partition codes, and Trombetti Zhou codes. These are the process of finding omega in these three different decoding algorithms. If we just summarize and compare these two decoding algorithm for generalized twisted Gabidulin codes and AGTG codes with TZ codes, we can see that the differences for the first kind of family is first, I mean, the coefficient, the zeros coefficient and case coefficients are somehow dependent, but in the TZ code, they are independent. And the first one, the problem is reduced to a projective polynomial in this form, but for the second family, the problem is reduced to solve a quadratic polynomial equation over FQN. So this is the difference, and we can see that TZ codes can be decoded more efficiently and with much lower complexity. There are two more applications for interpolation-based decoding algorithm apart from decoding of twisted MRD codes. We managed to decode Hermitian arithmetic codes, and this paper was presented in BFA 2021. And also, we managed to decode Gabidulin codes beyond half the minimum distance, again with interpolation-based decoding. The second paper can be found in arXiv. Thank you so much. This is everything from my side.